A student is investigating forced vertical oscillations in springs. Two springs, A and B, are suspended from a horizontal metal rod that is attached to a vibration generator. So this vibration generator is causing this metal rod to oscillate up and down, and that causes these two mass spring systems to oscillate up and down as well. We're told that the stiffness of A is K and the stiffness of B is 3K. So this is K, this is 3K, those are those two stiffnesses. Two equal masses are suspended from the springs as shown in figure 10. The vibration generator is connected to a signal generator. The signal generator is used to vary the frequency of vibration of the metal rod. When the signal generator is set at 2 Hz, the mass attached to spring A oscillates with a maximum amplitude of 2.5 times 10 to the minus 2 and has a maximum kinetic energy of 54 millijoules. So the fact that it's oscillating at a maximum amplitude means that the mass spring system A is resonating. So this frequency that we're applying, the 2 Hz, is the resonant frequency. Something resonates when the driving frequency is equal to the natural frequency of the system. So 2 Hz would be the natural frequency of mass spring system A. We want to work out the spring constant for A and the mass m suspended from it. So we want to work out what K is, we want to work out what m is. We have the frequency, so this is the natural frequency of mass spring system A, that's 2 Hz. We have the maximum amplitude, which is the 2.5 times 10 to the minus 10, or 2 rather, and we have the maximum KE, which I'll just call E. Maximum KE is the 0.054 joules, just converting that from millijoules to joules. So let's think of equations that can help us work out K or M. There is this one, time period is equal to 2 pi root m over k. We have the time period, or we can work it out. Time period is 1 over frequency, that'll be 1 over 2 or 0.5 seconds. But we have two unknowns in this equation, mass and spring constant. They're both unknown. If there's two unknowns in our equation, we can't solve for one of them, so we can't use that, at least not just yet. Let's think of energy next. So maximum kinetic energy is equal to 1/2 m times V max squared, and V max is equal to omega A. So this equation then becomes 1/2 m times omega squared A squared. That omega A, this is the maximum speed for any simple harmonic oscillator. Sub that into what we have here to get this expression for max KE. So looking at the equation that we have over there, we have the max KE, we want to work out mass. We don't have omega, but we can work it out. So omega is equal to 2 pi f. The frequency was 2, so this will be 4 pi. And then we have the amplitude, which was the 2.5 times 10 to the minus 2. So then, if we rearrange this equation for mass, we get mass is equal to 2 times E, all divided by omega squared A squared, which is 2 times the 0.054 divided by omega squared, which is the 4 pi squared, and then times by A, 2.5, 10 to the minus 2, all squared. This gives us 1.0943, and then the numbers in our question are given to 2 sig figs, 2 Hz, 2.5, 54, so let's round this to 2 sig figs as well. So that will be 1.1 kilograms. Now to work out K, we have M, now we can use the equation that we have over here. We have M, we have T, we can just rearrange this for K. So T squared is 4 pi squared m over k, squaring both sides of that equation. Now we can switch the k and the t squared. We get 4 pi squared m over t squared. So that would be 4 pi squared times the mass, the 1.0943. Notice how I'm not rounding it too much so I don't get a rounding error. And then divide by t squared, which was 0.5 squared. That gives 172.8, again round to 2 sig figs, which would be 1 70. And for part 2, calculate the frequency at which the mass attached to spring B oscillates with maximum amplitude. So basically, what is the frequency at which the mass spring system B resonates? So that is the natural frequency of mass spring system B. So we know from the previous question that the frequency of mass spring system A was 2 Hz. We also know that when going from A to B, the spring constant tripled. If we go back to the diagram, we were told in the question that the spring constant of spring A was K and that of B was 3K. So when going from A to B, spring constant triples. So we can use proportionalities to work out the new frequency. So frequency is equal to 1 over time period, and time period is equal to 2 pi root m over k. So if we're using proportionalities, let's disregard all the things that are constant. So 2 pi is constant, the mass is the same for both springs, so T is then proportional to 1 over root K. Frequency is equal to 1 over T, so if I do the reciprocal of both sides of this proportionality, I get 1 over T is proportional to root K, and 1 over T again is frequency, so frequency is proportional to root K. K triples, so frequency will then get multiplied by root 3. So now we know the factor by which K changes, replace K in the proportionality with that, and change the proportionality symbol into a multiplication symbol. Frequency gets root 3 times bigger. It was 2 Hz to begin with, now it's root 3 times bigger, so that'll be 2 times root 3, which is 3.46 Hz. Round to 2 sig figs, 3.5. And on to 7.3, the final part. Figure 11 shows how the amplitude of the oscillations of the mass vary with frequency for spring A. The investigation is repeated with the mass attached to spring B, and it's immersed in a beaker of oil. So 2 changes. 1, we're using spring B, so that means that the spring constant triples. And 2, we're immersing it in a beaker of oil, so that means we're increasing damping. It then says in the question, a graph of the variation of amplitude of frequency for spring B is different from the graph in figure 11. Again, because of those 2 changes, we're changing the spring constant, we're increasing damping, and therefore this graph would be different for B than A. And the question is asking us to explain the 2 differences in the graph for spring B. Okay, so if the spring constant triples when going from A to B, as we worked out earlier, the frequency has increased. The frequency was 2 Hz to begin with. That was the natural frequency of mass spring system A. Now it's gone up to 3.5 Hz. So, where before this peak was at 2 Hz, now it'll be at 3.5 Hz. Again, because the spring constant has tripled. So that will be our first difference and explanation. So the peak shifts to 3.5 Hz as this is the new natural frequency with the spring constant tripling. And then for the second difference, if we increase damping, remember that damping is a force that opposes the motion of the oscillator. This does work, takes away energy from the oscillator, transfers it to the surroundings, and that will decrease the amplitude of our oscillator at all frequencies. So the amplitude will be lower, and that's because energy is transferred away from the mass spring system due to the work done by the damping force. So the amplitude is lower at all frequency due to the decreased energy of the oscillator, as the damping force causes work done which dissipates the energy of that simple harmonic oscillator.